So we should be able to do a bunch of stuff with probability. So we always go back to so we have a set answer for last time. You have some specs are given to you, and you have to meet them. This table is a sample space for experiments for those probabilities. So, because you have a relatively high chance, you have a chance of passing it 3 times. You have a 12.8% chance to pass it twice and fail once. And you can see that kind of 1, 2, 3 times. Fail, pass, 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 fail, pass, and fail, fail, pass, fail, pass, pass, pass. So you have the same exact curve 3 different times. And I just want to yay! You have a 3% chance to fail twice but pass once, and fail 3 times. And from this, based on the laws of statistics, you can figure out the chance of all of these based off of the two. Okay. So if you have a 8% chance to pass, you can figure out each of these individually by just taking them by each other. 0.8 times 0.8. And something in the middle, all of those will always add up to be 1. The sum of all your probabilities on these will add 1. So a random variable is a function that assigns a real number to each outcome in the sample space. We have the probability distribution. What is our chance of this event? And this random variable is the probability distribution that is that specifies a list of possible x values along with the probability of each. So back. Random variables, probability, and how many times it occurred. And ideally, this should be representative of this. Ideally, when you run it. But if you see 3, 4, 5, 6, 7, 8, 12. So 3 out of 12. Oh, I see. It's passed twice, passed once, passed twice, once. By the way, some of the tables here are absolutely atrocious, and I apologize before you even get them. So there is a chance that a bit so X is the number of bits received in the next 4 bits transmitted here. The probability is given. So here is that X, and here is the chance of errors in each of them. So at X equals 0, you have 1, 2, about a 5%, 3, a little less than 0.5%, and 4 is 0.0001%. Just a way we can describe it. And you can describe it either as a table here or as a graph like that. And you can see was relatively small. So for discrete random variables, X with all kinds of probabilities, the function of your f of x is always going to be greater than 0. The summation of all the sum of your probability. If I add all my probabilities together, they're going to be 1. Makes sense. I can't have more than 100% chance of anything. And the f of I, so that function is actually my probability at that x value. So, wait, I don't know why they're so. So if you have a variable x, there's a number of wafers that you analyze large particles. Assuming the probability that the wafer contains a large particle is 0.01, right here, and that the wafers are independent, which is important, it's assumed that one wafer is not going to contaminate the other. What is the probability of the distribution of x? So at x equals 1, we have a probability that 1 occurs right there, 0.01. So P is a wafer in which a large particle is present, and A is a wafer that is absent. So our sample space is P, AP, AAP, AAAP. So you're just adding another wafer that doesn't have one. So our values of x are 1, 2, 3, 4, up and up and up. In order to calculate it, you take your chance of a large particle, 1, times the probability that there isn't. And as you have more wafers, you just add another 99.99 to make it bigger. So the next biggest one is at 0.0099, 0.009801, 0.009703. So it gets slightly smaller, smaller, and smaller, and smaller. So here's a general formula if you care. But as you do this, you see a change in how things. That's out of order, isn't it? And as you just essentially what you end up having as you do it is something like this, which just slowly decreases over time. But even then, the area under this right here would all equal 1. So as you get larger and larger sample sizes, eventually. So the cumulative distribution function. Right here, right? This was taken from the very beginning, right here, right? So our initial distribution here, our cumulative distribution essentially just takes this value here and adds this value to it to give you your new value. That's all it is. They're making this much more complicated than it needs to be. When you do cumulative distributions, so the probability of 3 or fewer errors right here. Well, if I have a probability of 0.9999 at 3 as a cumulative function, then my when somebody says, what's my chances of this happening? And what are my chances of failing this class? Well, let's see. Was it 59 or 69%? B, is it B or C? What? C? So I think everyone at 69.49. And everyone above that. Because I base it off of the work you do. So this bugs me mathematically. I didn't make it. Sorry. because they're subtracting. And the reason it bugs me is they're subtracting right here 2 points at f of -2, right? But at -2, you have an open dot and a closed dot. I know what they're doing and why they're doing it. But you're not supposed to do that. But anyway, what they're trying to do is they're trying to figure out how much is so up here they have at when a value is less than -2, you're going to do it. When you go from -2 to 0, 20%, and 0 to 2 is a 70%, and anything above a 2 is 100%. So that's what they're looking at, is how I change based on what. There had to be a better way to do that, but when I see that, I'm like, but there's a hole in the graph, and you're continuing the function below. You can't do that. Sorry, I teach algebra. It really bugs me a lot. So that's what they're trying to do, is they're trying to show you those thresholds, because I'm pretty sure this is probably where some calculus happens. At what point do I start going up? And you can kind of see on here where you would have a distribution function leading up to the top, which actually would go straight here. So a cumulative distribution function is given as that. Summation of your so is equal to the probability of big X is less than little x, summation of the f of x values. Your f of x will always be between 0 and 1. That's a given of any distribution. You can't have more than 1. You can't have less than 0. And then when x is less than y, your function of x is going to be less than your function of y. And that's where this ends up. And there's a very simple way to do this. So we can, with some very basic math, calculate the expected mean, expected variance, and expected standard deviation given it. I have done this on people's papers because they know the right results, or more importantly, to see whether or not they're lying on their distribution. So if I were to take the expected values of x for each distribution, add them up, I'll get my mean. If I were to take that x value minus the mean for each individual and square it, add them all up, I'll get my variance. And take the square root of that, I'll get my standard deviation. So what that means, let me go, I have an example here. This table, terrible, do not use it. I will take this table and make it make sense because they don't know how to make tables. Oh, come on. Escape. No. So what I'm going to do is go into Excel and turn this into something sane. So I have my x value, actually lowercase x, at 0, 1, 2, 3, 4. Then I have my probability of x at 0.6561. 0.2916, 0.0486, 0.0036, and 0.0001. So those are my probabilities and my X values. So what I would do is I would plug in essentially this X value into my probability and do that for each one of them. And I would get basically the mu. Expected mu is what I'm calculating. So I take my X value, which should be my observations, times my probability, and then I copy them down, all the way down. And then add them all together and get my expected mean. So all I did is take that X value, take it times my probability of obtaining that value, then add all those together, and that's my mean. What they want to do from here is they're trying to take that, taking your X value minus my mu, and then squaring it, then adding them all together. They're not very good at this. Because this is, this is terrible. So expected sigma. So right at this point, I'm going to calculate my sigma. So I have my expected mean minus my X value squared. Make sure when you do this, if you're going to do this, that you lock in your mu value, because it's not going to change when you copy things back, but everything else will. So then I just add this together, and then I get var. So this is your variance. Take them and add them all together, and gives you a 22.8, which is different than theirs. Why is it different? Oh, I did that wrong. The x minus 0.4 squared. Oh, times fx of x. Is that right? Sorry, making sure I get this right. Oh yeah, times. Make sure you do the times your variant, that value, which gives us a variance of 0.36, and then a standard deviation is the square root of your variance, 0.36. So our standard deviation is going to be 0.6. So we have a mean, expected mean of 0.4. This table, which I could even make bigger by doing each individual step, is easier to read. What they did over on their screen here is had you x and then x minus 0.4. I don't know. They should have put this here and then use this to calculate that here and this here and this. Basically, that's that. The third, fourth column should have been. So this lets us find those values. So from there, and our variance can be considered to be expected value of a specific function of x. So our variance will be something that provided we have so if we have number of squared number of basically squared. All we would do is take our x squared, our x value, square it times by the probability. You add them all together, you get a so we're kind of doing the same thing, except what we're trying to do is take this value here. So we're squaring it, so we square everything here, 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 and here. So all those x values get squared. And that's based off of what you have. So you have the same x value, you plug it in, and you go. So a uniform distribution. This is the most boring thing to draw in the world. That's a uniform distribution. So if you have, I think somebody asked, they're trying to do D12 rolls for the D&D nerds, the barbarian dice. Yeah. One. So anybody who's never played D&D, you have all kinds of fun dice. And ideally, if you have dice that like you, unlike me, you would get a distribution like that. But that's what I expect if I roll a dice, if it's a 12-sided dice. I expect more or less to get the same number. It just might take more rolls. The chances of each one happening are based on n. So if I have 12 sides on a dice, my chances of rolling a 1 are 1. Normal gambling dice. Same thing. The probability of each one is based off of how many outcomes you have available. So if you have the A to B, and A is going to B, there are B minus A minus 1 values. Therefore, f of x is 1 over B minus A plus 1. So this is how you find the mean and variance. So the mean will be kind of hard to see on here. The e to the x is equal to b plus a over 2. And then the variance, b minus a plus 1 squared minus 1 over 12. I'm sure someone did a lot of work on this to get these numbers. But I don't normally work with how things work. So if we your sigma. So our expected value of x is take your 48 and 0, the two ends, add them together and divide it by 2, 24. Makes sense, right? If you have an equal chance of all the variables to find our standard deviation, you take the difference between the two, 48 minus 0. I just don't know it. I probably will look at it later. So on average, the number of lines should be about 24 if you have a good uniform distribution. Makes sense. But because you have a standard deviation of 14, you can good if you only have 48 lines, by the way, because within 2 standard deviations, you're out of lines. So you might want to not do that. So a binomial distribution, slightly different. X is equal to numbers of trials that represent special binomial random variable between 0 and 1 with n positive numbers. The probability mass function is of right here of n of x. Let me go back to the highlighter. And not the highlighter, the laser pointer. N of x of p to the x minus 1 minus p n minus x for positive x values to up to n. For those for the constants a and b, this is the expansion form. So once again, we're back to those wonderful, wonderful permeations. And all this the same basic thing. So if we have 10, choose 3. 10 permeations. You're looking at almost 4 million. And don't forget, the 0 permeations is always 1. So why do we do this? Because you have weird I recommend not having to do these by hand because they're not fun. If you have a sample of water, it has 10% chance of containing on the probability that in the next 18 samples, exactly 2 contain the pollutant. So we have a probability of 0.1, a sample size of 18 to 2. So 0.1 squared, or 18 to 2, times 0.1 squared minus times 1 minus 0.1, the 16th power is equal to 163 times 0.1 squared times 0.9. So the 16th power is equal to about 28%. Or that right there. I would recommend that right there. When you set this up, this card is, where's my Excel? You can have, it's going to ask you for sample size. This is what I always end up doing. Sample size, you have goal, chance, because that's what it all is asking for. Then you set up as a binomial, so equals binom. Binomial distribution. So the first one will be the success. Second one is the sample size. Third is the chance. And then you got to do false. Then you set the sample size, goal, and chance. And then it just calculates it for you. This is how I usually set up the sheet. So that because the binomial distribution will always be set up that way. So you might as well just set up a binomial distribution. So you can just change variables and go. Looking at the next one, determine the probability that at least 3 samples contain the pollutant. So on this one, well, we're looking at less than or equal to 4, so we can just change this. Oh, I could. See, this one was. Oh, exactly. So this is exactly. This is at least. Nomial equals binomial distribution. Once again, we have, oh, it's 1 minus, sorry, equals binomial distribution. So we have 18, sorry, oh, number S, sorry. We have 18 or 2, 18, and the confidence, and we're looking at true. So if we need to do exact or 3 or less, we just change it to 3 because we don't care if there's 4 or more. We're looking at, so what I did is I took the probability of having 3, so the third, added them together, and it's 1 minus that number. That's what I'm doing. Because if you look really quick at a graph of binomial distribution, as you get higher and higher, you get more of the successes. So you're trying to figure out how high you can get back down. And once again, yes, use Excel because life is really annoying to do all that math. And after that, it's just you're just trying. This one you're looking at between 7 and 30, or you just do the same basic math. You just use different formulas. So the binomial mean is your n times p. That's, I mean, that's simple. You do something very close. The variance is your n times your p. And I'm looking for and then 0.9 will be my standard or my variance. So on this, I have mean variance. So my mean is, once again, n times p. Chance times sample size. My variance is going to be my mean times 1 minus your probability. So 1 minus chance. Easy enough to calculate. Like I said, use computers. Don't get it wrong. It's for that was for the variance. For the square root of the standard deviation, you would have it. No, that was literally for the variance. For the variation, or for the standard deviation, you will have to square root in order to get that value. So this is one with n of 4 and a p of 0.1. We'll give you those values. This is not that hard of math, but once again, I always, whenever I have easy math, personal choice. So binomial distribution simply have a fixed number of trials, and you have a random number of successes. A geometric distribution has reverse roles. You have a random number of trials and a fixed number of successes, usually 1. So this is the formula, 1 minus p of x minus 1 times p. So this is a Bernoulli's trials, independent trials with constant probability p of success. The random variable x that equals the number of trials until the first success is geometric random variable. Except the only time I've ever used this is for p corrections whenever you have something that has a high chance of success. Bernoulli's correction factor, it's kind of annoying. So wafer contamination. So once again, we have that wafer contamination of 125 wafers need to be analyzed before the process is tested. But we have a sample size of 125, that equals 125, and the probability is 1. So 1 minus your probability is 0.99. 1 minus, or 125 minus 1 is 124, and then your normal probability. So you're looking at a probability of 0.0028. So let's see and you could actually kind of set this up if you want. So if you wanted to, you could just set this up, these two values, and then just change this and see how your distribution changes up and down based on how many wafers you need, which would be something, which is kind of cool actually. So if I had, not you, if I had probability P is 0.1, P P that is 0.99. So what you can, if you wanted to look at it, is you could just do this if you need to do it, and then you have your X values. Deal equals that. And that just gets this. So all I'm doing is I'm basically setting up that 0.99 times 0.1, and I am at 10 for this case, I'm at a 0.99%. So almost 100%. So let's see how that would change. Yep, and then I'm almost up to 10. So if I do this till 100, it should. Oh, and it didn't do it, of course. And as you see, it goes up to essentially 0.1 or to 1. It's just a way, and if I change these around, because if I, it should be equal to 1 minus that. Because I always like doing reference cells. So if I change 1.2, for instance, I can see how it changes. And it's kind of a cool tool because then you can say, if I play around with probabilities or things, like if you have to deal with this, how do you set up this number? It's really good because if the problem is you have a bad day, I have a bad day, really goes up at 10 points of something happening, you can tell many people like, this is done now because like in 3 hours, it's going to be 50% written down. They don't like that. And people don't like that because essentially they need to get that down now. Because they don't like a lot of people fix now or bad things happen later, they'll fix now. So setting up these spreadsheets actually can be really very useful. Current slide. Because remember, this is determining one event. And if that one event is something that's very major, like safety, that's a very important thing. Your mean is 1 over your probability. And your standard or your variance is 1 minus the probability. Probably the easiest math you've done in years, isn't it? And once again, to find the standard deviation, which is what the next one says, all you do is take that variance and take the square root of it. Because it's nice. Okay. If we have a probability that a bit is transmitted through digital transmission channel is received in error is at 0.1. So the probability of the mean the variance would be that 0.9 minus 0.01 or 90. So the standard deviation is about 9%. If you're doing this, if you have like 3 or 4 of these problems, after the section 2 on how to do the spreadsheets. You could also do these on MATLAB. I'm pretty sure you can. It's not cheating if you can make the computer do it for you. So, lack of memory. Oh, dear Lord. So my current project works in HTML graph and you got all the void words, and then do a distribution graph of his most common words. And I can't even trick the computer into thinking I have that much physical space, let alone memory. So yeah. So lack of memory is actually a major problem. So all troubles are independent because of memory. You cannot remember how until your next success is started, and any problem the idea is you're not going to wear out the system. This is not always the case. If you like, R has like 2 to 4 gigabytes. So, yeah, this is actually do it. You run into problems where you have to run repeated measures in order to get it. This is your probability is so low. I have 4.5 gigabytes of DNA that I have to run this through. It's, guess what? It's going to take forever. So there's some mathematical shortcuts. For transmission of the probability error remain constant, so we can say we run into problems because of how many times we have to run things. So the probability that a bit is transmitted in error is 0.1. Suppose 50 bits have been transmitted. Does that mean the number of bits? What is the mean number of bits until the next error? So we would assume the mean number of bits transmitted to the next error transmitted is the same as 10. We would assume that it would be 3 more because of the probability. Same result as the mean number of bits after consider system. Because we assume that with the next 10, we're going to have, we assume 10 could happen before, but we don't know. A negative binomial distribution is we have random variables is a number of newly chosen coordinates. So we have x minus 1 and y minus 1. So what does this do? Instead of 1 over p, we have r for our name. We add the r function to the we have that r function. So that r function once again is to a specific number of successes. So instead of just doing 1 success, we have a specific how many successes do I need? and then let me run that binomial distribution until I get those number of successes. So camera flashes again. So if we have X as the number of the probability X is less than or equal to 5, and X is a negative binomial distribution with the probability of 20%. So we have then we run it through here, we essentially get a 0.58. I love summation so much, really. So, a hypergeometric distribution. I have never use this when you have a finite population without replacement. The reason I didn't is when I took stats, this was for people who were literally restricted to what they had in nature. So I took biostats, and I had people who were doing wildlife ecology. Can you make more rivers? Can you make more rivers? No. So they kind of stop. And they can't sample it because they're doing selection bias. So they have a specific number they can draw from, and they can't make more. That's kind of what this is for. So there's literally an entire branch of statistics of how do you deal with really, really hard problems. Got to run into that too. Anybody safety engineer? Anybody want to do that? So my uncle had this job. His job was at one time to destroy all the nerve agents in Utah. Are they making more nerve agents? I hope not. So once he ran out, population. So we have a set number of objects of n. K objects, which is the successes. N minus k are the failures. So how much are you succeeding versus how much failing? The sample size of little n is selected randomly without replacement from your population, where the k is less than the population, and your sample size is less than your population. So the random variable x that equals the number of successes in the sample is a hypergeometric random variable, and the f of x is equal to k of x minus x, which is a fun thing to do. And that whole formula will get you something like this. So this is manufacturing parts. Good example. If you're manufacturing, you're not going to make more parts than especially in a car run non-stop. If you make 850 parts and 50 of them not make confirmation, 2 parts are selected at random without replacement. For testing, A and B denote the events that first and second parts are non-conforming respectively. What is the probability of both parts conforming? One part does not conform and both parts do not conform. So 50 choose 0, 800 choose 2. So essentially of the 50 parts you get, how many of them were the chances of 0 happening? And then 850 over 2. So this is the math you're going to have to do on all of them. And then you do 50 of 0, 82, or 802, 51, 801, 52, 800, 0. Run the numbers and you get your percentages. And once again, all of these will add up to 1. And this could be done on Excel too, believe it or not. Kind of annoying. But. So another example, 100 parts from a local supplier of a circuit board and 200 parts from a supplier in the next state. If 4 parts are randomly selected without replacement, what is the probability that they're all from the same supplier? 100, 4, 200, 0, 300 over 4. So at that point, because you're doing the 100 on the 4. And they're all from the same state. And it's like, so 2 or more parts, you do probability. And that gives you your base percentage. And probability that 1 is the probability of 1 4. But when it's only asking for probability of at least 1 part, you might as well just take the probability of 4 from the other and only do the math. How we figure out the mean? Same way. Times your population size minus your sample size. Your population size minus 1. And probability is K over your population size. Okay. Okay, so next we have the Poisson distribution. So Poisson is when you have a random variable that equals the number of ends in the Poisson process of the Poisson variable with parameters of 0 less than lambda. So e to the negative lambda t times lambda t x over x permeations. Not following general curve. You have a lot of very, very low values, and as you go up really quickly, they go away. I didn't use it until I did stuff on pathology. I started looking at disease data. Because in a population, you may have a lot of individuals that don't get the disease. How many people die right now? 90% of the world. So our distribution for all this is going to look like that. That's what every disease ever always looks like. And that's why I silently scream at the computer screen every time I get dumb enough to go on Facebook and look at all those memes and all those bad posts. Because people they don't But this is expected. That's exactly what we expect. The issue with COVID is it is a lot higher than the flu, is a lot higher than almost every disease out there. And it's scary. So yeah, wear your mask and wash your hands. So wire flaws. a kind of random along the length of the line. So most of the time, copper is very, very dependable, right? It usually doesn't have copper. So most of the time, it's in a good state. So X is a random variable that contains the number of flaws of length of T millimeter of wire, and the number of flaws is about 2.3 per millimeter. Find the probability of exactly 10 flaws in 5 millimeters. Not going to be very good, by the way. So you just plug and plug it in. 11%. I do believe, and I'll have to check on this, that there is a Poisson distribution in Excel, and I would recommend doing it because I don't know. If not, maybe I'll put it. So the probability of at least one flaw in 2 millimeters of wire. So 2.3 times 2 is 4.6 flaws. So probability of 1 minus probability of 0, 1 minus e to the negative 4.6 gives you 98.99. Which makes sense because if you expect a flaw in every 2.3 millimeters, you're going to have a probability. So that kind of makes sense. So my number actually makes sense given my question. So this is the very last slide. Everyone cheer. So our mean, second mean is that lambda times t, and our variance t. Which makes sense. If that's the distribution we're looking at, we're going to expect to have a mean. And the particle flow capital of the Poisson distribution with a mean of 25 particles per square centimeters. The variance is about 25, and the standard deviation is 5. Now, if the variance of the data is much greater than the mean, then it's not a Poisson distribution. Which makes sense. If I have something like this, as more of a very bad skewed data set. So if you have a bigger variance, you're not going to you just have to. Are there any questions on that?